Section 5.4, decision trees. Decision tree classifiers are attractive, particularly when we care about interpretability. With the algorithm, we can see details of decisions and classification. As the name suggests, we can think of this model as breaking down the data by making decisions based on asking a series of questions. It is invented in 1959. Decision trees are commonly used in operations research, and also they are quite popular in machine learning. Let's look at a typical decision tree. Work to do for the question. If it is yes, then we stay in to finish the work. If not, then we may consider outlook. If it is a sunny day, then go to beach. If it is a rainy day, then you can ask a friend if they are busy. If yes, then you are alone so that you can stay in. If they are not busy, then you can go movies together. This is a decision tree and about an activity on a particular day. Here we have the key idea to decision tree. Start at the tree root with the whole data set and split the data so as to result in the largest information gain. That means that we are using information gain function as an objective function, and we try to maximize it. Repeat the splitting at each child node until the leaves are pure. That means that in the last moment, each node has the points belong to the same class. Until then, we can do it, the splitting. And in practice, this can result in a very deep tree with many nodes, which can easily lead to overfitting. So typically, we set a limit for the maximum depth of the tree. In scikit-learn, I believe the default depth is 5. Okay, let's consider now decision tree objective. Decision tree also needs to incorporate an object function. And here the object function is the information gain and maximized at each split. Yeah, this is the definition of the information gain. Now DP is the parent data set. Okay, F is the future. Let's look at first the data. Here we have DP, the data, that is DP. Okay, each row is representing a data point, and here a column is a specific feature. So when we split the data, and we are using a feature. Now from the parent data set, and we'll choose a feature, and by using the column, the information from column, we try to split the here. Now information gain is defined in this way. Impurity of there's I is impurity measure of the parent data set. That one is already decided. Now we try to split from parent node. We try to make, for example, 2 children. Now impurity of, okay, so that DP is split into now D1 and D2. So that impurity and this child and that child will be computed, and here multiplied with the proportion nj is the number of samples in the jth child node, and np is the total number of samples at the parent node, so that the point proportion is multiplied, so it is a sort of average child impurity, and that is subtracted, and we will try to maximize it. So here, information gain is simply the difference between the impurity of the parent node and the average of the child node impurities, and we'll optimize it. Okay, so the lower the impurity of the child nodes, if it is smaller, then difference will be bigger, larger, so that information gain becomes larger. The larger the information gain. But in reality, because of simplicity, we are usually using binary decision trees. That means that we try to get 2 children rather than more than 2. In general, you can make more than 2 children, 2 and more, but because of simplicity, we try to get only 2 children for each splitting, and that is common practice. Here now, there's a left one, right one. Then impurity of the parent data set is now subtracted by the average of children's impurities. But a children has 2 nodes. There are only 2 children. Okay. The information gain is based on the choice of impurity measure. Here we have examples. Here, commonly used in binary decision trees, that the first one was entropy measure, that is defined in this way. Now, what is PI? That is the proportion of the samples that belong to class I for a particular node T. So we are working on the node T, so that ignoring this portion, focus on I, so that is ith node, the proportion, and times log to pi, and summed, because it is less than 0, is less than 0, so that along with minus, the whole thing becomes non-negative. For Gini impurity, it is defined in this way: pi times 1 minus pi and summed. Once we expand, then summation of pi must be 1 and minus, now pi squared summed. For classification error, that is 1 minus maximum of pi. To understand these impurity measures, we need a bit of mind simulation. Let's focus on when the number of classes is 2. Okay, for entropy, it is a maximum if we have a uniform class distribution, and it is 0 if all samples at the node T belong to the same class. That is exactly this case. Now in node T, every point is in class 1, so that this value is 1, but P2 must be 0. Along with that, here the entropy will be 0. And here uniform class distribution, then P1 and P2 are 0.5. By using the values, you can reach at here the entropy 1, that is maximum value. Now for Gini impurity, and that is maximized if the classes are perfectly mixed. That means that P1, P2 are simultaneously 0.5, and by using this equation 1 minus 0.5 squared, I is 1 to 2, so that 1 minus quarter and quarter, so that result is 0.5. That is the maximum value of Gini impurity. In practice, the entropy and the Gini impurity result in very similar the classification. Now, for the classification error measure, it is less sensitive to changes in the class probabilities of the NAS, so that it is good for pruning. However, it's not recommended for distant tree algorithm. So mostly people are using entropy or Gini impurity. Now, once you are using distant tree algorithm, and if we want to see the detail, then the algorithm will print out such graph, distant tree. And here, in each splitting, there is question petal width is less than or equal to 0.5. Along with this question, it is decided. Now also here another question, and based on the question, and it's now split, and again, and with this one split, and so on. For each split, a question is involved. The question is now, how can the distant tree find such questions? That's now our question, and let's see how these questions are selected. So that is now the distant tree split rule. Along with this rule, the question will be selected. For each and every feature in the parent data set, so each level, now, okay, here, that is DP. Now, we try to split this one into two parts, okay. Now, each row of DP is representing a point, and here now, a column is a specific feature. So, for every feature in Fji, so that is now ith point and jth feature, so that this value is now in jth column and ith one, that one, for each one. That means that for every entry in the data set, so therefore that one, we make a question. So we want to split the data set into left child and right child. So we want to ask question in this way. So same column, J is the same, but K is different. So for now we try to here, now along the column, we ask such questions so that once it is satisfied, then we put it on the left. Once it is not satisfied, then we put the data on the right. So that here that is fixed. From here, we compare with this value, and once it is satisfied, then this point will go to left. And for the next point, this value and that value will be compared, and then if it is not satisfied, then it will go to right side, and so on. We do that way, then we can make two children, DL and DR. Now, for each one, we compute the impurity, and so that we get IDL and IDR. Now we get the information gain. So for each of point, each of feature, we have the corresponding information gain. So for every point we do that. So this entry, that entry, that entry, that entry, and for the second one, again we do that, right? So for every entry, we measure here information gain. So IJ is moving through whole data set. So we have this information gain. Among them, now we choose maximum one. So the one which makes maximum, so that PQ are chosen, so that here pth data point, that is pth data point, and now Q's feature. Okay, we decide this one. Now by using this one, here we split, so that there is now here along the column, Q's column, along the column, if that is now satisfied, then is left child. If it is not satisfied, then it becomes the right child. So in this way, we try to split the parent data set into two children data set. So in that way, for each split, the inequalities, that question is made. Okay. Here, so in this maximum, in this equation, is often happens when one of the child impurities is 0 or very small. That means that once one side is pure, then the information gain is maximized. Okay, so that after splitting, we try to make a children as pure as possible. Okay, that's the end of the first part, and we'll continue in the second part. Thank you.